Hey guys, welcome back. We're going to continue talking about work and energy, and in this episode, we'll talk about potential energy. So, something can have potential energy based on a couple of different things that we're concerned about. You could have something that has potential energy because it is a certain height above the ground. You could have something that has potential energy like a toy that's wound up, like the constant acceleration cars that we had. Or you can have something that has energy because there is a spring that is stretched or an elastic band that is stretched. All right, so I have a bowling ball here. This is Lotsie. And I'm going to do work on this bowling ball. So to do work on this bowling ball, I'm going to apply a force directed up, and I'm going to displace it up. The force that I have to exert on Lotsie to lift it up is exactly equal to its weight. So my work is equal to the weight multiplied by how high I lift it. It only matters how high I lift it vertically. It doesn't matter if I go one side or the other. So very often they'll call this the height, or they'll call this delta Y. Now, once Lotsie is up here, Lotsie has more energy than it did on the ground. And that energy that it has is potential energy due to gravity. This is dependent on both Lotsie and the Earth because there's a gravitational field that Lotsie is feeling. If Earth isn't there, Lotsie doesn't have any potential energy. This is what the formula is for potential energy due to gravity. I'm going to put Lotsie down. So depending on what your equation sheet is, you'll either have delta UG equals mgy or mgh. It varies between the two AP classes. This is going to require a mass Earth system. So Lotsie by itself doesn't have any potential energy, requires those two masses. So if they ask you for how much potential energy just Lotsie has, it has none. So considering the Earth mass system, what's the potential energy of a 5 kilogram bowling ball at the top of the tower? So this is going to be equal to the mass of the bowling ball, the acceleration due to gravity, and the height. And again, for this, we don't want to put in negative for G, right? Because we want to define whether this is positive or negative based on the relationship between the displacement and the forces. So when I'm talking about this mg here, I'm talking about, the force it would take to lift it up. So it's 6,500 joules. And this is positive. In these situations, you usually get to pick what you want the reference point to be. And if I was doing this problem, I would say, I'm going to make 0 be the bottom of the building. All right, considering only the mass system, what is the potential energy of the bowling ball at the top of the tower? This is 0 joules. And this might seem weird, but AP seems to have this as something they want to focus on. That you need to realize that the system can be just the bowling ball, and if it is, it doesn't have any potential energy. The bowling ball by itself can have other types of energy, which I'll introduce in the next part. So the potential energy is going to require two masses. Okay, so this potential energy for any two masses is equal to negative G M1 M2 over just R. Does this look familiar to you? Yeah, it does. It looks very much like so if you think about what we had, we're saying that work is the same as energy. And we're saying that this is force times distance parallel. So you can see that if I took my force and I multiplied it by a distance, that I would cancel out an R and I end up with G M1 M2 over R. Why is it negative? I've told you guys about a number of conventions we had. They're just things that we agree upon so we can study physics the same way. We talked about it always being an inertial reference frame. So we're in a non-accelerating reference frame at all times. That way Newton's laws work. We talked about assuming there is no air resistance for the most part. Unless they tell you that it is. So the reference for this is that the potential energy between any two masses is zero at infinity. So at an infinite distance away, the potential energy is defined as zero. Now, we haven't talked about conservation of energy yet, but if you think about LHC again, when I lift LHC up and I give it an amount of potential energy and I let it go, I can turn that energy into energy of motion. And it's going to be moving with a certain amount of motion by the time it gets to the ground. The higher I go up, the faster I would expect LHC to be as it got down to the tiles. So if we're saying that at an infinite distance, the potential energy is zero, if I let those two masses go, they're going to be attracted to each other and they're going to accelerate towards each other for an infinite distance and get a certain amount of speed. If I bring them to a closer distance, anything that's less than infinity, they're not going to be able to go as fast. So what that tells me is I have less energy. So less than zero is negative. So all of our energies and we're going to use this for space things mainly. So it's anywhere in the universe. So we're not really worried about LHC. We're worried more about comets and stars, planets and stars. And again, I can explain this in terms of work as well. So if I have these two masses an infinite distance away, they are attracted to each other. So I'm going to have to, if we're saying that they're this far away and I want to bring them to a distance, I would actually have to exert a force on this mass this way to displace it that way. Because they're already being attracted. If I want to bring them together without it speeding up, I'd have to exert a force that's equal to what they're attracted and slowly bring it in. Which is weird, just like I said, when I lower this, I'm actually exerting a force up to lower it. And so since the force and the displacement are in opposite directions, that makes my work negative. And if we're saying that work is the same as the change in energy, if my work is negative, the potential energy is negative. So any way you want to think about, if you want to think about the reference as being zero, and go from there, that it has to be less. Or if you want to think about the work you'd have to take it from infinity to that point. Those are both explanations that will work. All right, so I have a star and a planet. Might be a little blurry. It's in elliptical orbit. What graphs would show the energy of the planet and the energy of the star-planet system? All right, so in the absence of outside forces, the amount of energy in a system is constant. It can't be created or destroyed. So that means that if the second column is our combination, it can't be this one or that one. And so it's either this one or that one. The planet itself would have no potential energy. It would only have energy of motion, which is kinetic. Would the speed of it change? Yes. It's going to turn out that the closer this comet gets to the star or this planet gets to the star, it's a planet, it's going to go faster and faster. And it should make sense, right? Because there's a force between these two, and this force that it's exerting on it gets bigger and bigger as it gets closer to its orbit, and then smaller and smaller. So a bigger force on the same mass is going to cause acceleration, which means it'd be going faster and faster, which is this choice. If you look at all of these, the total energy is negative in every choice they give you. That's because the potential energy is going to dwarf any kinetic energies you have in these types of systems. So the total energy is always going to be make the total energy negative because of the potential energy being negative. And again, that's just how they define it. So the planet will only have kinetic energy that will always be positive and change based on how close it is to the star. It's always positive because the V is squared. The star-planet system will have a constant energy, no outside forces. It'll be negative because the potential energy is much greater than the kinetic. A sled slides down a hill with friction between the sled and the hill, but negligible air resistance. Which of the following must be correct about the resulting change in the energy of the sled-Earth system? The sum of the kinetic energy and the gravitational potential energy changes by the amount equal to the energy dissipated by friction. So again, and we'll talk about this, we have conservative and non-conservative forces. The energy has to go somewhere. Sometimes it goes places that it's not easy to get back. It's hard for us to get back energy from friction. That is true. The gravitational potential energy decreases and the kinetic energy is constant. It doesn't tell us it goes down at constant speed, so I don't know if that's true. So the potential energy does decrease, but I don't know what the kinetic energy does. The decrease in gravitational potential energy is equal to the increase in kinetic energy. This is not true because they're telling us there's friction, so it is definitely losing some energy there. There'd be heat created. The gravitational potential energy and the kinetic energy must both decrease. That's not the case. We don't know if it's speeding up or slowing down. They don't give us any indication besides that there is friction.